Welcome to part 4 of the tutorials about CalcLink. In this part, I would like to show how kernel sharing works. That is a mode in which CalcLink can be operated in order to use one kernel between the Mathematica frontend and the spreadsheet frontend. And if a calcpad is used, that actually means that we end up with 3 frontends that have access to the very same kernel. That's particularly useful to share data or function definitions, or make function definitions in one front end and have them accessible in the other and shuffle back and forth between these data and function definitions. Then I would like to talk a bit about the graphical expression browser, the graphical tree browser, and say a few things about how error handling is done in CalcLink. So we begin by launching CalcLink. That will again bring up an empty spreadsheet. And in order for this to work, we have to say calc enable kernel sharing of true in the Mathematica frontend. What this command does is basically to prepare the kernel we have just launched to be in the mode that CalcLink can connect to it externally. But once this is done, we can immediately connect to it from the spreadsheet, and this time we say connect rather than new kernel because we already have a kernel that we simply want to connect to rather than create a new one. So this now allows us to make function definitions, symbol definitions in one front end and have them available immediately in the other. For example, here we define a variable, and that is immediately available in the Mathematica frontend. Likewise, we can make a definition in the Mathematica frontend and retrieve the value in the spreadsheet. Now, if a calcpad is used, we can also use that in order to access the same kernel. So here we also have var1 and var2 known to the calcpad, and we can also make a definition here that is then available in all the other frontends. This is particularly useful if large amounts of data are to be shared or stored or manipulated in these 3 frontends. For example, huge amounts of data could be retrieved with the database package or the web services package or with the XML functions in Mathematica or just through other import functions that can obtain data all over the web and then can be displayed or manipulated in all of these frontends. For example, the Mathematica frontend could be used to use the data with a manipulate interactively, and the spreadsheet could be used to display tabular data from a database, or whichever way people would like to manipulate or view the data. Next, I would like to show the graphical expression browser. That is a function called calctree, and we can give it simple expressions or involved expressions. We will start with a simple one. For example, CalcLink calctree of pi square shows us a graphical representation of pi raised to the 2nd power. We can use more complicated expressions. For example, this is a 3rd degree polynomial, and when we submit this, we can interactively inspect the nesting structure of this polynomial. We can make these expressions more complex. For example, the plot command creates a graphics expression. Let's just plot the sine curve. And we get a graphics expression, and we can now interactively expand and collapse those nodes that we would like to inspect. There are several nodes that we would probably like to look at and others that are not of particularly interest. So this is one way to interactively drill down and zoom in to see those parts that are of interest. Plot3D creates a graphics 3D expression. So now we are creating a really involved expression. And we immediately get a new window with the tree representation that we can now inspect any way we want. We can zoom in and drill down on any level that interests us, and always collapse those nodes again that we don't want to look at. And given that all three frontends share the same kernel, we can now also submit calc tree from the calcpad, for example, a simple second order polynomial from the calcpad, where we get a new pop-up that shows us how this expression is structured. Next, I would like to show the graphical symbol browser. That is a function called calc show symbols, and this function shows us all the Mathematica symbols that are known to the kernel. In a left column we have the name of the symbol, in a right column we have the value of the symbol, and in a row called filter text we can now use regular expression matching in order to filter out those expressions that we would like to look at. For example, if we enter pi, then we can see all the symbols that contain the letters capital P and lowercase I anywhere in the word. If we say plot, we see everything that contains plot anywhere. Now, given that this uses regular expression matching, we can now filter this down further. For example, this is all Mathematica symbols that begin with plot. This shows us all Mathematica symbols that end with plot. We can get as fancy and involved as we want. For example, this would show us all Mathematica expressions that contain the word plot but don't begin with a capital L. So this would filter out list plot and log plot, for example. Particularly useful, I find a regular expression to check the lowercase symbols that we have. Particularly useful if you obey the convention that Mathematica symbols from Wolfram Research should be uppercase and your own should be lowercase. That way you could easily detect leakage in any packages here that you write. And we see that we only have a few symbols here. Some of them are our own from this session. The other ones are the CalcLink symbols. Actually Java objects that allow the more advanced Java programmer to use JLink and inspect these objects further. Another one would be, for example, \d, that shows us all symbols that have a digit character in them. And again, this shows us the Mathematica symbols as well as our own symbols. Finally, for this part of the tutorials, I would like to show a feature of the error handling. For example, you could submit something in Mathematica that does not make any sense and does not have any representation in the spreadsheet as integer, rational, or string. For example, if you want to compute the square root of just the symbol list, this makes absolutely no sense in Mathematica, and instead of giving you an error pop-up that is modal, which means that it blocks the interaction and you have to deal with that particular pop-up, then CalcLink shows a separate window that is not modal but simply contains a list of all the errors you have created in that session, like in a blotter style where several errors are simply listed rather than inhibiting your interaction. This is quite useful because the error that you have made could actually have been done several times. So if you submit the same error several times, it doesn't block your interaction with it, but it simply lists everything in a blotter that contains all the error messages of that particular session. That concludes part 4. Thank you.